تاع المشاركين. لن أطيل عليكم رجاء التزام الهدوء من أجل مواصلة الحدث مع المحاضرة المقبلة للسيد أو البروفيسور مروان دباح. مروان دباح اللي راه معنا. مروان دباح مرحبا بك. تحية مروان دباح اللي جاء من أبو ظبي من الإمارات العربية المتحدة. وأترك لك المجال مرة أخرى رجاء شوية هدوء وخاصة في مدخل ومخرج القاعة لو سمحتم. تفضل.
السلام عليكم. شكرا في هذه الانفيتاسيون هذه. وشكرا ثاني نخبه هنا محمد ولاوي اللي بلو لا في لا معليش. So I شحال عندي الوقت؟ 30-40 minutes. Okay, I'll try to be fast in explaining. So I'll switch in English to explain. So the title of my talk was mostly about 5G and AI, which has been the heart of basically all the research I've been doing all these last years. But I called it my journey or my AI journey to give you a bit of a hint of how I started my career, how I ended into AI. Of course, everybody's here and we have a lot of people because AI attracts a lot of people because it's a domain where basically everybody feels that he understands things. And in general, people will tell you that whenever things are written in Python, this is machine learning, but whenever basically things are written in PowerPoint, it's AI. So I'll do things in AI so that I'll explain a bit what is AI about. But I was told to explain a bit also about my career to motivate more of the students who come here to listen a bit more about our careers. And I think this is also the purpose of the conference, to give you a bit of a highlight how things have been coming into what's happening today. So as far as I'm concerned, my career started here in Algeria, where I was a student in Lycée Aix Descartes, which is Lycée Cheikh Bouamama. And then I went to France for what we call classe préparatoire. And there I did my classe préparatoire in a lycée called Henri IV. And then I ended up in something called École Normale Supérieure Paris-Saclay, now it's called Cachan, working on physics. And my introduction to telecom was a bit of an accident because I was not aimed to that. I was going to go more studying physics because I thought that was the main goal. And we were around basically around 97, something like that. And in 1997, you have to know that telecom was getting a boom. That's the start of all the highlight that you know about. And accidentally, I started looking at calling from France to Algeria, which was a bit of expensive at that time. I mean, making a call at that time is not at all what you have today. And making calls was very expensive. And one of the tricks that I used to do, at least to give some kind of information that I came back to my house, at least when I was a student, basically was just to call and hang the phone. Because when you call and hang the phone, you give one bit of information. I think you're all used to that whenever you arrive somewhere. What you do, you just call and hang the phone to say to somebody that you arrived. And because you didn't make the call, so you don't pay for it. So it was a neat technique to use basically the network without paying, because you could make a call, hang the phone, and basically you could still warn a person that you had arrived at home, especially when it was night. And for my mother, that was quite important. I think all of our mothers here are quite basically protective and want to know if you came back at 11 or midnight at home. And so I thought, well, this is great because I can send one bit of information by just calling and hanging. But I could send more bits of information by doing this protocol. Meaning I can send the letter A with one ringtone, I can send the letter B with two ringtones, I can send the letter C with three ringtones, and then wait and then re-ring. And by the number of ringing tones, I can encode my information. And I said, this is a great idea because I could make calls using the classical network without paying anything. So I said to myself, let's build a system. And that's what I did. I started building the system, meaning you encode letters to the bits and ringing tones. So, of course, when you look at that system that I'm trying to tell you about, well, it's not basically latency sensitive in the sense that nobody's going to wait before you make a message or send a message. It will take time if you want to send a message where people would read it. But if you want to send SMSs, or if you want to make faxes, which fax were extremely expensive at that time, this is a great system because you could wait like 1 hour, but still get the information for free. And at that time, sending an SMS or sending basically a fax from France to Africa was extremely expensive. And so I built a system. And of course, that's where you start looking at how you do it. And I started building and said, oh, the A is going to be 1 ringing tone, a B is going to be 2 ringing tone, a C is going to be 3 ringing tones. And then you go on like that. And then I said to myself, no, because there are some letters which come more often. You know what I mean? Because typically the letter E comes more often in English than basically other letters. So you would encode the letters with less ringing tones. And so, of course, people told me, yo, Merwan, stop doing that. There's already a guy called Shannon who thought about this. You don't need to do that. So they told me, just go look at his books and you're going to see it. Which turns out that I started dealing with information theory to understand how you encode letters to bits to make the system more efficient. So I built the whole system, extremely happy, and I said I'm going to be extremely rich. That's the first step to a startup, because I said to myself, what I'm going to do is basically build a system which reads basically the text that I want to send, converts that basically with the modem to ringing tones, and sell that type of system. And then on the other side, people just plug in from the phone to the ringing tones and get the fax or get the message. You do it at a computer. So I built and I was extremely happy and it worked. I said to myself, I'm going to be the most richest man of the world because it's a huge market for all the faxes. Everybody needs a fax at that time. Now you can certify documents differently. And of course, I started looking at how to start getting funding. And of course, when I started getting funding, one of the guy or the VCs came to me and said, this is a great idea, Merwan, but basically you are, at that time they didn't call Uber, but you're disrupting the system because basically you're benefiting from a network without paying. And you have to know that before you, people thought about it. In fact, the first phone systems that were created in the world, people said to themselves, are we going to make people pay when the phone rings, but nobody answers? So that was a big question in the first telecommunication network, which was built a long time ago. Because you use a network to ring a phone, and they said, if we don't make people pay, then there's going to be some smart people who are going to use that kind of ringing to do the system. So they thought about that, and you have to know that what they did as a solution, they said, but we cannot make people because at the end he's not going to answer. And so paying for somebody who's not in the house is a big problem. And so what we do in telecommunication network, they have desynchronized the system. What I mean desynchronizing, meaning that when you have a certain number of ringtones somewhere, it's not exactly the same number on the other side. They cannot basically guarantee that. And basically, if they cannot guarantee that, it means it can ring 2 times in a certain place, but it's not going to ring 2 times in the other place exactly for a phone call. So you're not aware of that, of course. And this is sometimes why people tell you, oh, it rang only 3 times. You say, no, I rang 3 times. And sometimes there's some disagreement because they didn't want to have people like me who disrupt the system. And so it was a bad experience because it was the first startup that I built. And of course, it was negative because, of course, I didn't understand really the rules around those systems. By the way, we have to go back also to the system before. You have to know that also when we built the first network, all these questions of privacy were also a big issue. The people who built the first network were asking, well, if you let ringing a tone without somebody accepting it, it's an issue. Because basically, you are intrusive in his life, meaning you make the phone ring in a house. He never asked for it, and it rings. So all the issues that we're seeing today in AI have been already asked many years ago. In fact, in the first 1900 systems that we built. And of course, when you ring a phone, it has also an impact because if the guy does not answer, it reveals a lot of information on the guy. So there's many possibilities. Either he's not at home, so of course you can steal him. Second, of course, he doesn't want to answer. So if he doesn't want to answer, there's also some information you're getting about the guy. Why doesn't he want to answer? So the question of ringing tones is quite similar to what's happening around here. So that was a real basically shock for me because, but that was a bad experience. But I learned a lot because I learned that before getting into building something, you need to understand basically the market and how the system, the real guys who have did it. But in any case, that was my first time getting into the telecommunication business. 6 months after, I had a roommate who went to Berkeley for his master. And basically, he calls me at 3 o'clock in the morning. So that was my second experience, which was also a bad experience. Because everybody talks about successes. I want to talk about failures. And failures, of course, that's what basically drives you to be good. And so the guy in Berkeley, that was in 1998, calls me and tells me, Miroir, in Berkeley, there is a Syrian guy who did a huge startup. He's making huge money at the moment. And it's called Lucky Surf. I said, what is Lucky Surf? He told me what you do is very efficient. You have a web, and then basically what you do, you play some numbers. And if the number gets appears, then you earn $1 million. And if there is no number which appears, you get $0. And I said, but how does the guy make money? Well, in fact, every time you click, there's ads. So it was based on ads. So you had ads, and what you had to do is just the kind of little boxes, which is basically what you have today in what we call La Française des Jeux and stuff like that. Basically, you start playing, and you just need to click on an ad. So for you, it's not a big issue because you just need to click. If the number appears, you're happy. And he says, Mirwan, well, what we need to do is just import the concept today in France. There's nobody who has done it. We have to do it immediately. He said, this is great. I'm going to be rich. Second thing, I can be extremely rich. We need just to redesign the website. We need to redesign the whole system, and we do it in. So we did that. We registered in company in Nancy. It was called Loto Gratuit, meaning what it means, Loto Gratuit, meaning free Loto, where basically you have an app, you have a website, and you start clicking on it. Then we took a huissier, which had a number, and each day the number was getting generated by this huissier just to be protected, and then the people were clicking. So we started doing 2 months, and it started to have a lot of clicks, and we were extremely happy because we started having a lot of people going. And then I was still a student. We had rented a small office. We get a call from La Française des Jeux. And La Française des Jeux tells to me and the guy, so we start having, we want to have a conf call with basically the partners. We were 3. My roommate was called Jean-Louis Guénégaud. And basically he tells us, okay, well, you have to know that in France, there's a monopoly of La Française des Jeux, which was the case before, monopoly. And so you cannot basically play on this, otherwise you'll go to jail, and we're going to be issuing basically lawyers to go to see you, and you start to get in jail. So of course I got freaked out, and I said to myself, I still want to do a PhD or something. I don't want to go to jail right now. And my other partner was more bold, by the way. He was more bold. He said, no, we should not stop. We should continue, Mirwan. This is bullshit. We should take lawyers and go in front. I said, yeah, we have to take lawyers, but it's going to take 3-4 months. And of course, La Française des Jeux is such a big company. How are we going to do it with the La Française des Jeux? It's impossible to do that. And he told me, no, Mirwan, you have to do it. And I was like reluctant and saying, no, I don't want to go to jail, And I still didn't have my papers, by the way, meaning I didn't have any kind I had a carte de séjour, and I said to myself, all of these are going to be negative points on me. I don't want to get into that. So we started discussing, and unfortunately, I convinced him to stop. I said to say, we have to stop. And we go to La Française des Jeux, sell what we have, basically, give them to them and see if we can get a good price, and then we go out. And he said, no, I don't. Okay, finally, we sold what we had, and La Française des Jeux just stopped all the different lawsuits against us, which was a bit of a surprise for me. And then 2 weeks later, there's another company which pops up and start doing huge business exactly on our same model. That was what happened. So, and we were all shocked in the sense that we built the whole system. Another company 2 weeks after did the same thing. And when we went to do that, unfortunately, it was a big mistake not taking lawyers. You have to know that in France, there's a monopoly as long as basically people don't pay for a ticket. Meaning if you pay for a ticket, then basically there's a monopoly. It's like La Tombola or something if you pay. But if you don't pay, there's no problem. You can still do those websites, stuff like that. And that's where exactly that market went in. So the second basically kind of experience was bad because I learned that whenever you have a problem, you need to take lawyers. And it's very important to be protected and go in. You have your right to go forward. You should not miss it. I mean, even though you may be afraid, which was a good experience for many things that I had after to do, where basically when people tell you something, then you should double check every time around that. So again, I was asked to continue my story and go forward before I get an introduction on this. So then, of course, I started looking at telecom, and telecom was becoming a big thing at that time. And 1999 was a big boom. And so I didn't really know what to do. And I said to myself, well, maybe I'll go to work something related to telecom. And then basically by wandering around basically a forum, a guy from Motorola comes to me and tells me, look, what do you do? I told him I do physics, but I'm interested in telecom because I did this thing. He said, if you want, you work at Motorola Labs during 3 years, and you do your PhD, and we pay for you. I said, this is great. I'm going to do a PhD during 3 years, work for Motorola. And he told me, we're going to put you in a corner because you're weird. We're going to put you in a corner. You're not going to interact too much with the teams, and you're going to do some things that you like. And I said, okay. Well, I come in the physics domain, and there's a big topic called random matrices. And I think maybe that's good. And said, we don't understand what a random matrix is, but I said, it's a physics stuff, things like that. And I started working on that. And for some reason, that was a breakthrough. I didn't even know about it. I worked on it, and one of the application was related to 4G, a system called OFDM. And basically, I worked on those systems and started to build papers, stuff like that. And around 2001, there was another mistake. Motorola comes to me and says, well, you've been doing great work now. We want to sign a contract with you, because that was a 3 years contract PhD, by the way. And I said, no, let's wait a bit, because I'm not even sure I want to continue. So I didn't sign the contract, which is what we call a CDI, start to wait. And basically a couple of months later, there was a big bubble. Big bubble. Nortel went down, all the companies went down, and Motorola started laying off. And he told me, Mirwan, you have to go. You're a great guy, you're a great scientist. So what it means here is that even if you're great, whatever you do, you can be fired the next day. They told me, we really want to keep you, but we cannot keep you anymore. You have to go. So I said to myself, what I'm going to do, and that was 2002. 2002, there was not a single job in the market. No job at all. No job at all. Nothing. I was looking, I sent my CVs everywhere. People were telling me, you're a great guy, you're a normalien, like they say, you are the top of the top. We don't have any place for you. We're sorry, things like that. And so surprisingly, I get an email from a guy in Austria one day and tells me, the paper you wrote is one of the greatest paper I saw. I said, okay, that's great. And he writes me and says, I want to have a discussion with you on the phone tomorrow. Can I talk to you? And what I mean by that is that as a researcher, you have to be careful. When you write a paper, it's not just about writing papers. It's about basically getting your next job, because the people who will read your papers are your employers. You never realize that there are many people out there that are called headhunters. Professors are headhunters because that's how they recruit postdocs, for example, but other type of headhunters which come to you and say, we're going to take you. And so the guy, of course, tells me, I read your paper. I want you extremely to work with me in Vienna, and I'm going to give you a flight tomorrow to come to Vienna for interviews. So of course, I go to Vienna, and basically there I'm blown up by everything, because in Germany, compared to other places in the world, whenever you are a doctor, you are like a hair doctor. You have a super high rank in the society and stuff like that. So the first day I arrived, they start showing me stuff. And so I start my work. And so, of course, I signed the contract. And the guy tells me, of course, we want to take you, Mirwan, because what we read on your papers are just top notch. And we want you to work on that. So I arrived there in September 2002. And in September 2002, the first thing I do is that I sign the documents. I spend a bit of a week of understanding how the company works, and then I go see my boss and tell him, okay, what should I do now? What do you want me to do? And that was a real surprise in my life, and that's the last time I asked somebody what I should do in my whole life. He looked at me and said, Mirwan, are you a doctor? And I said, yeah, I'm a doctor. And he told me, you should tell us what we should do. I'm not here to tell you what you should do. We recruited you to tell us what we should do. Why do you come to see me? I said to myself, he's right. I mean, I'm supposed to tell him what we should do because he employed me. Otherwise, coming there and says, this is really surprising for me that you asked me this question, Mirwan. I'm like, okay. And so from that day on, I never ask anybody what I should do. Meaning that whenever I come in a place, I'm more first of proposition than asking what to do in that place. So I work, of course, 1 year there, 1 year and a half. In fact, it was more than a year and a half. And then I get a call from an institute called Eurocom, which is Telecom Paris in the south of France, located in Sophia Antipolis, which is a great region, by the way, in terms of sun, beaches, and stuff like that. And I get a call and telling me, we have an assistant professorship position there, and we would like you to take it. And I'm like, it's going to be difficult because I have a very good stable position in Vienna. And it's true that the salaries that you had as a doctor in Germany, if you had experience, are extremely high compared to what you have in France. And so, but then I thought to myself, Nice is close to Algeria in terms of flight. It's 1 hour flight. We all have this problem of parents being here and you want to be far away. And I said, I'm going to give it a try, which I think was maybe not the best thing to do in my life. But in any case, I said, I'm going to give it a try and get a position in Eurocom. But this is something else also quite important that I need to mention for the young generation is that applying for work in your life, I think you should do it only once. What I mean by that is that when you graduate from university, this is the first time you should apply for work because nobody knows you, which is normal because you're starting your career and starting to apply. But I think if you're successful in your career afterwards, you should change only by people calling you to change work. And this is how you measure the success of your life. The measurement of the success is not by the fact that you apply, but it's by the fact that you become so visible that people call you to change work. So the first time only you should do it is after your master, after your PhD, which is normal because nobody knows you. But then if you have the need to every time to apply, then you have to ask yourself what's wrong that I'm doing in my life. Because you should change jobs only by people who hunt you and tell you, I want you to work for me. Which turned out exactly what happened to me in all the cases that I'm going to give you here. And that was also a big lesson for me, is that you change jobs only because people call you to change jobs. And this is how you measure the success. Otherwise, you have to ask yourself, what the hell am I doing in my company at the moment? Because it's not visible enough, or I'm not doing outstanding work, or it's not known enough so that people tell that I need to go somewhere to work for them. And so I go, of course, to Sophia Antipolis, and I think this is also important to highlight, is that doing an academic career is not an easy stuff. Many people say that academia is easy because they have vacation, stuff like that. But it turned out to be an extremely good experience, but it's not an easy. And I'd like also to congratulate all the professors here, how hard it's as a work. Starting my life in academia turned out to be hell in the sense that I never had nearly a vacation. People think that professors have vacation, things like that, but they read their papers on the plane. They go on vacation with always their bags with full of papers, trying to correct what their master students is doing, what the other is doing. So they nearly have no vacation. Second thing, of course, there's also a level of sacrifice, which is big. And the third thing is it's a startup which never finishes. So it's extremely, I would say, as a career, something that pushes you far, but there's a lot of things that you don't know behind. A professor does not only teach, he does research, he does recruitment, he does PhD committees, he does financial support, he does HR. There are 10,000 work that he does at the same time. In a company in general, you have a focused work and you only do that. And I know it because I've been changing from companies to universities. But as university professors, you cannot know how many different tasks you have to do, which is basically managing a startup, which is your own team. And at the end, it turns out to be extremely difficult. But there's something I want to highlight, which was quite funny when I became an assistant professor, is that, of course, I applied and coming to university, and I said to university, okay, I'm coming, and it was basically in the summer. Can you find me an apartment where I can, go? And they told me, no, we can't, because that's not the purpose of university, to find apartments. We recruited you, you have to find your own apartment. I said, no problem, I'm going to find an apartment. And I think this is also important for you, that when you go somewhere, there are all barriers that you need to go through. And one of the barriers that I realized that when I arrived in France in 2003, end of 2003, I started my contract and went to get an apartment. Getting an apartment in France was crazy. I went there. They told me, well, Mirwan, you're an assistant professor. It's great, but we cannot rent you because you need a garant. I said, okay, I'm going to find a garant, which is a guy who guarantees basically the fact that you're doing. So I found the garant, and I came back, and they said, no, but now we cannot rent you because you're in période d'essai, which is basically during 3 months. So of course that was a shock. I was at the hotel, so of course I went to university. Well, I'm coming and starting next year. I don't have an apartment. Can somebody help me? And then there was somebody who answered and told me, no problem, you can stay in my place. I have a small place, but you can stay in my place. So I go in this guy's place, which was a very nice guy. And of course he tells me, well, this is my bed and this is the floor. And so and I have a bag, what we call sac de couchage. You can take the sac de couchage and it was very small. I said, okay, I'm very thankful because I don't know where to go. You know, I'm assistant professor. What was funny is that the guy was nearly never here because he was partying, going outside every time, and I rarely saw him during at least 3 weeks, and that was the vacation time. And the first day I start my courses at Eurocom, he was sitting in the first row. He was my student, just to let you know. So it ended up that during 2 months, I was the professor sleeping on the floor, and my student was sleeping on things until I had my period d'essai done, which tells you also in a career there's a lot of steps that you need to go through, which are never easy in terms of achieving what you want to do. So to make the story short, of course, I spent 4 years, which were extremely fulfilling at Eurocom, and then I got another call from Supélec at that time. There was basically the dean who was looking what we call for a chair holder. Alcatel-Lucent decided to put a lot of money at Supélec and decided to open a chair on a topic related to 4G. And they called and they said, okay, Mirwan, we think you're a good candidate. Can you come for an interview to go to Paris to take the chair? And that's how, of course, I started a lot of work, more telecom oriented with more industry during more than 7 years, 2014. Another thing also, which was quite surprising, is that when you're a professor, and that was a very good time of my life, you train a lot of extremely good guys, top talent guys. And one of the top talent guys that I trained, of course, were coming from various places, and one was Chinese. And that Chinese guy went back to China, worked for Bell Lab Shanghai, came up to a top level position, and then moved to Huawei, and got a top position in Huawei. And so in 2014, I get a call, same thing, from this guy, tells me, look, we're looking somebody to head what we call the 5G program of Huawei, and we think you're the good guy to do it. And I said, no, I don't want to go to China. It's not possible for me to go to China, at least at this moment. He said, no, 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 no worries. What we'll do is open a research center for you in Paris, and you will lead that research center. So it ended up that I moved to industry, which was a good, fulfilling time. And during 7 years, I took over the 5G program of Huawei. And this is, of course, how I got to be more known in industry. And for some reason, which I think is overestimated, people think that I'm the one who built the 5G of Huawei. I think there's a lot of things behind that are not related to me. But it's true that Huawei was a bit like a follower in 2014. And one of the big things that we did in Paris was build up what we call the polar codes, a type of error correcting codes with my team, which basically went into the standard. And of course, then the system, I mean, the company got a lot of awards, and for some reason, I became in the news in China nearly everywhere. So if you go to China, you can read the news sometimes around Mirwan for this Huawei stuff. And same thing around 2019, before the 5G program finished, Huawei asked me what I should do because 6G was too early. It started in 2021, to be honest. And they told me, we have 2 years. What do you think we should do? So I pushed for the establishment of another center called the Lagrange Center, which is more a mathematics center, because I think that you need to bring a lot of more money in terms of fundamental research. So we built up this center called the Lagrange Center, which is quite notch center with medal fields in Paris, and where I had the opportunity and, of course, the pleasure to be the head of some medal fields, which is unusual for me. It was a great time working with them during more than 2 years. And which is quite important, because I think in a successful circle of research, you have knowledge, you have money. The purpose of academia is to convert money into knowledge, which is extremely complicated. I give you 1 million euros. How can you convert that into knowledge? Which is quite surprising. You create knowledge from money. It's extremely crazy. And then you have the industry, who has to be smart enough to convert money, to convert the knowledge into money. And so the quite successful, I would say, circle is when, of course, it's quite efficient in how you do it. And so, of course, I told them this is the way we should do. And of course, it was accepted. And it still exists, by the way, the Lagrange Center. And in 2021, I'll talk about it, I started building basically a center in Abu Dhabi, where I was called again to open a center there. And I thought it was a good opportunity to see how things work in the Middle East, because I think after my Chinese experience, it was quite important to go there and start learning. And I'm going to talk about what we did there, and especially basically on building centers. And also, I think it's also important, especially for many people here, is that when you do research, that you have always pressure. It's not always an easy task because people think you get a good result. The magic about research is basically about finding the right balance between what I call quick wins, mid wins, and long wins. You need quick wins in the sense that investors who are behind you want to see results, so you'll never avoid that. You need basically with the quick wins to solve what we call the long hanging fruits. I'll talk about some of those long hanging fruits that we did. And you need also, of course, also long wins because that's the purpose of research. The purpose of research is to open the gates, is basically to do disruptions, the big thing. But nobody's going to wait 10 years before basically you do the big things. They're going to knock on your door day and day to get more pressure, knowing what's happening, what you get the result. This is going to be annoying. However, if you can release from time to time some little results so that basically you calm the pressure, then it's okay. So the real magic is how you can get some quick wins without wasting your long wins. Because if you do quick wins by diverting your attention, it's not good. So within the road of the long wins, you need to find the smart way to capture some quick wins to make the people a bit happy. It is as if I told you that you work on a research topic, take off industry. You work on a research topic, and during 10 years, you publish nothing before you bring a big thing. Publishing nothing during 10 years, because you're working on the big theorem that will solve basically a big issue, will cut you out from the community. You're not going to conferences anymore because basically you're not submitting papers. So you need within that trend to look at some things which are easy to do. You have a couple of papers. They're not like disruptive, but at least basically they're bringing a bit to the community while you're working on that big problem that you want to solve with the big risk that you're taking, by the way, of that. And I think the smartest people that I saw basically in research are the ones who have the right balance in understanding that how I can do the quick wins to basically calm the pressure while working on this long win, which is going to bring me the big prize or going to be the big medal or the big startup or the big disruption about what we're doing. And I think it's very important to understand these things when you start a career with what I'm going to say. So let's start basically, although I don't have a lot of time, I know I get pressure, so I'll go fast, unfortunately, around these things. So my talk is going to be about this journey, and of course the journey started with telecom. I think you're all familiar with what we call the generations, and especially 2G. To be honest, I was very skeptical about working on AI around 2015, because that's around 2014-15 that I started to bring my big interest. Of course, everybody knew about AI since a long time. I don't need to do the history of it. But basically, I was skeptical because as many people who do optimization or mathematics were good in models, and you don't really understand why you should take over all the modeling that you did for what we call data-driven approaches. There are many reasons, but something struck me, and that was exactly what I'm going to talk here, which happened. So I think you're all familiar with 2G, which was built as a network. GSM is one of the biggest highlights that you know, but it's not the only reason, which is basically related to mobile for voice. In general, a generation takes 10 years, by the way. And from every 10 years, a new generation which appears with basically some KPIs. This is the definition of a generation. Then you have technologies which fulfill those generations. For example, 2G, for which the KPI is mobile for voice, branded like that. If you go on the numbers, they're more precise. But it's mobile for voice. Behind you have various technologies which fulfill that. For example, GSM is one, but you have, for example, in the US, something called IS-95. So there's many technologies which fulfill a generation. This is very important for you to know. So 2G was mostly mobile for voice. 3G was basically, people do not remember, but what we call mobile for data, with basically a focus related to visiophonie. You have to know that visiophonie, after listening to somebody's voice, people wanted to see, but it turns out that those ugly it was not smartphones, phones that we had were extremely bad for doing that and basically did not know the success. 4G came in 2010 with the big option of doing what we call mobile for internet, meaning something full IP, which was great, meaning having what we call a wireless ADSL experience with mobility. And it's very important to have mobility every time because you can have a wireless ADSL experience everywhere. And basically you go outside, you still have that. And my main interest in AI came with 4G. And one of the big issues that we had in 4G, people are not aware of that, is that the voice quality in 4G is crap. It's very bad. Why? Because it's basically an internet structure. Voice in 2G is a technology. Voice in 4G is an application. It's like WhatsApp. We have a system called Voice over LTE. That's what we built. And so when we sold the first phone, everybody was complaining because basically when you call on a 4G system, it goes like an IP system. And an IP, there's packets, it goes through the whole thing. And so, of course, when we start building that thing and we start selling the phones, people went to complain. And the majority of operators in 4G, even now, there are some many operators who do that. You have a system called CS fallback, circuit switch fallback, meaning when you make a call, you switch on 3G and 2G, and whenever you browse on internet on your phone, you're on 4G because the call quality is bad. It's not as good as GSM. You sell people a phone and then they don't call. What is that? Even though you tell them to browse. So this is how we solved it. But by 2014, 2015, the pressure started to be more because a lot of operators wanted to do what we call spectrum reuse, meaning that they wanted to shut down the 2G, 3G network and start using the spectrum for 4G. And so I had a lot of pressure from my former company to start solving that problem. And it was extremely hard to solve. Extremely, because basically it's extremely hard to model an end-to-end system where you have basically IP. Because it's not about SNR, signal to noise ratio. It's not about basically things that you have classically. It's about where the servers are, where the core network are, where the security protocol is done. So it was extremely hard to solve. I'll talk about it, and I was able to solve it the day basically there was data. What it means is that we start having a lot of data related to voice over LTE performance for various network that we had. And then the question was quite easy to improve a system based on all these data that we were gathering because I was not able to do what we call an end-to-end optimization. The other thing which came in after is, of course, mobile for things. And I think you're all familiar with 5G. Although with 5G, you have to know it's not about just things. It's three things. It's related to evolve mobile broadband, which you're having today, meaning more data rate. Having, of course, the Internet of Things. And the other one is what we call the ultra-reliable low-latency communication, which brings you basically the fact that you can use low latency for Industry 4.0 with also reliability, because reliability is not possible, at least with what you have in a 4G. Sometimes the calls do not pass. What's interesting, of course, this has opened the realm of big data because the things that we want to deploy, basically, of course, they're bringing a lot of data back in. I don't have time to talk about the kind of technologies that we built behind, but it was very interesting experience to build all these systems, and especially basically on the realm that related to mobile for things and IoT, because there was a huge battle for people who are not aware in the IoT business between 5G, LoRa, and Sigfox, which were other companies which were building things similar. And today, what's important is that we're trying to understand how AI basically is revolutionizing the system and how the network infrastructure can help basically build distributed AI systems. And this is what we call mobile for intelligence. Because we know that by 2030, 2035, there's going to be more and more devices embedded with AI. And there, it's not going to be about human communicating to humans, machines to communicating to machines, but intelligences communicating to other intelligences. And there, basically, the kind of protocols that you need to build is totally different. And this is the kind of work that my teams have been doing, and we'll talk about them. I think I'll skip on these things, which are quite important, but just to let you know that in the telecommunication industry, AI is not new. Shannon had talked about it, had already designed the systems around it. And we all know one of the reasons already 1948, Turing and all the others, we did not make it, is the computing power that we have today. But I think it's very important for you. I know that I need to go faster around that. But I want to go rapidly. And learning, by the way, is also something not new, by the way. A lot of people tell me learning is new. For people who do signal processing, the godfather of the signal processing field is called Wiener. And learning was at the heart. It's control, meaning basically you don't know the model. So what you're going to do, you're going to have a feedback mechanism. And to the feedback mechanism, you're going to learn. In telecommunication, we learn, by the way. If you use Wi-Fi, for example, when you transmit the Wi-Fi, you have a system called ACNAC, acknowledgement, non-acknowledgement. So you send the packet, it's not acknowledged, you reduce your rate. It's acknowledged, you increase your rate. So the systems already exist, okay? So machine learning is a bit over there, but there's no notion of what we'll talk about it, which is the deep part. But you have to know that This is called in the telecommunication industry self-organized networks. It's something that we've been working on for many years. I can spend hours on this, where we build up a lot of algorithms related to systems which basically learn on the fly how to self-organize themselves. Of course, one of the reasons it didn't kick off is, and now it's kicking off, and it's called AI-based Sun, is that learning takes time. Okay? When you learn, it takes time. What it means by that, it means that, well, by the time you learn in general, it's too late. It's like as if you have an exam. You have many topics to learn, it's a lot of things to learn, and then you have only a limited time to exploit, so you have to be strategic in how you learn. So you reduce the scope if you have a limited time. And of course, the good part about doing deep learning, besides classical reinforcement learning, is that you can speed up the convergence. What I mean by that is that you have a memory. And the memory, with the data that you have, create a model. So next time you don't learn from scratch, you learn from all the past legacy. And learning from past legacy increases your convergence. Okay, I'll skip around that. I think it's blocked. Maybe jumping a slide. Can you jump a slide? Next slide, please. Okay, it's going to reappear. Yes. Yeah, I have many things to do, so this is why I'm going to jump faster, because I don't have much time. But all the slides will be available for you to go in detail once they appear, because there's a couple of important points I just want to highlight. I think I don't need to go through all the things, but just some quite important points. So I hope the slides are going to appear in a couple of minutes, and so there's a couple of topics on the telecom part with AI I want to mention. Another part also, which I think is quite important to understand. Let's go around. Let's see if the slides come back. They should come back. Okay, doesn't. So next slide, it doesn't go for the next slide. Okay. Let's. They're gonna appear in a couple of seconds. I see that Mohammed is it's already late. It's gonna go faster. I hope so. I hope I'm not the one delaying everything. No, it's okay. Good. So at least it's gonna be fine. 2 minutes? 1 minute. Okay, it's even faster than I thought. Yeah. So I think I'm gonna just mention some points which were quite important to highlight, and then of course on the slides, if you have questions, you can always write me. I'll give you more details about different parts about what we did, especially for people working in the telecom sector. If you want to get information, and also something that I want to highlight at the end, which I think is the next big thing in also the telecom industry, called the telecom brain, that we're working on it. And within that, I will talk about something quite rapidly, which is the quick win, which happened when you work on a long win. So one of the long wins I'm trying to work today on is what we call the telecom brain, which is basically building a brain that can manage the whole infrastructure around that. Okay, so let me jump on this thing. And with this thing, I think you will understand all the why it's so important today, and what you need to understand about AI, which then you can apply in your field. There was a couple of slides, but here you have two pictures which I think are very easy to understand. You have on the right a guy called Newton. I think you're all familiar with Newton. Okay, and on the left you have what we call a ballistic kick, meaning kicking a ball. So if you want to kick a ball and somebody tells you, find me the angle theta, such as the ball arrives at 100 meters. So if you go back to school, you look at Newton and you start solving Newton equation, and you can find the angle theta, such as you reach basically the angle 100 meters. Clear? Quite easy. You have basically a theory, you apply it. Second thing, which is maybe what North Korea is doing today, you don't have the theory. Okay? So what you do, you kick the ball like hell. Many times. Many times. And then basically what you do, you put in two columns. One column basically is angle, the other is distance. And then you stack all these things. Okay? And so next time somebody tells you to kick the ball 100 meter, what you're going to do is look basically in your database if basically 100 meter is there. So this has nothing to do with AI, nothing to do with machine learning. It's called data mining. So you're going to look and find if that distance is there. If you find that distance, you find the angle, the problem is solved. And so by doing that, of course, without knowing Newton, you are able to do a ballistic kick. Quite magic, meaning without knowing the theory behind. Where things become interesting is, of course, when the distance is not in the box, in the database. So you never kick the distance 100 meters. There, you ask any mathematician, it's quite easy. He will tell you what you'll do is what we call regression. Meaning if you have the distance 190, you have the distance 110, 100 is a bit of a mixture of both. And then you're going to look at the angle and you're going to do what we call some function approximation to find what is exactly the angle. And basically, you're able to solve that thing. In fact, what you're doing is basically finding the function such as x is a function of theta or theta is a function of x in this case. Clear for everybody? So what you're going to learn is you're going to learn that function. This is exactly what people do. And so you're going to do a function approximation. Doing the function approximation, this is a classical thing. Well, what you do an approximation. So you say, that function I will approximate by a polynomial, for example. So if you do a polynomial, it's finding basically the coefficient of that polynomial and becomes an optimization problem. That's why basically machine learning is optimization. What's good about the guys that I didn't show before, these three guys who are like superstars today, whenever they give a talk, it's like concerts, you have like 10,000 guys listening to them, is basically that they came with a hardware architecture, basically, on which the weights of the polynomial that I was talking, they don't call it weights, but it's the weights of the neural network, basically can be optimized. And we have basically also the frameworks to optimize them. They build also the tools to do it. So for you, it's magic. You have a black box. You put a lot of x's, a lot of thetas, and next time you have a new x, you get the theta. Clear for everybody? And so basically, without knowing Newton equation, you can solve the problem of Newton doing that. So what North Korea is doing. You can basically, of course, without knowing Maxwell equation, you measure Maxwell electromagnetic field in different points, find the new point, basically, by some kind of averaging that you're going to do around that. In fact, you don't even need to do the averaging. The neural network will do it for you. Of course, you need to have enough data. So you need enough. It's quite I would say simple to understand. You need a lot of sampling. So you need to kick the ball at some distances which are quite good to have the quite kind of regression that you're going to do. And so this is quite magic, but there are three caveats that you need to understand with that. And once you understood these three caveats, you understood, of course, where to apply this. The first caveat is basically, it's not easy to understand when you start in a field what are the input-output parameters of your system. In fact, in the example I gave you, I went quite fast. I told you there was a one-to-one mapping between theta and x. In fact, it's wrong. You need to know x and the initial speed to know theta. So the theta is a function of the initial speed, v0 and x. Example. You are super smart guys. You go in a startup which does health, and the guy comes and says, okay, we have a lot of data. Column first is cancer. Second column is temperature. Clear for everybody? And he tells you, this is the new temperature of a cancer. Tell me if he has this is a new temperature of a patient. Tell me if he has a cancer. It's evident for you that you cannot relate basically temperature to cancer. The question is, which column are you going to add? You're going to say, okay, I'm going to add a new column, which is basically ses antécédents. I'm going to see basically thing. I'm going to add the third column or fourth column, which is blood pressure. And the whole work of a data scientist today is basically to play and play and play and play hours and hours and days and nights and months to find basically what are the columns and then basically be able, because otherwise you're going to not be able to solve it. So this is the first caveat. It looks like magic because you can replace any kind of domain. I saw agriculture, things like that, but you need to have a bit of a hint of what are the right columns and what are the input outputs of your black box. Once you know what are the input outputs, then of course you can solve the problem. Second caveat of this technique is basically that it costs a lot of energy. Why? Because you kick the ball many times when it was a wind of 0, and the day you're asked to kick the ball, there's a wind of 5 kilometers an hour. It doesn't work. It means that you need to kick the ball for 1 kilometer an hour, 2 kilometer an hour, 3 kilometers an hour, every case that you need to do with enough sampling of your space so that you can apply the theory. So it's quite expensive to get. With Newton, it's easy. MA equal gravity. That's it. And you solve the problem. Here, you need to sample every time. Of course, you can speed up the problem. For example, transfer learning are techniques, meaning that if you learn something at 1 kilometer an hour, then basically learning something at 5 kilometers an hour will take you less data. I'll give you an example. Let's take languages. We know the example, if you have kids, it's very important to put them in music because music is like a universal language. So somebody who learns music then have a good aptitude to learn faster language. And then if you learn French, you have a faster capability of learning, for example, Italian, because the two bases or the two languages are correlated. So this is called transfer. What you learn in one domain, once you learned it, when you start a new domain, you don't start from scratch. You go faster. For example, in telecommunication, we've been using that. Just to give you an example. When you design a network, for example, in Paris, the base stations, how you do things, you want now to do your optimization in Marseille. Because the building structure is the same, you don't need to reinitialize all the system and relearn from scratch with new data, new users going around. You can basically take the learning from there to initialize your model and then train. Meaning the base station in terms of the weights of your neural network, they don't start randomly, they start exactly at the optimized point that you did in Paris. However, if you take the network that you build in Paris and decide to start building it in Abu Dhabi or even Algiers, because the buildings may be different, or even the desert, you need to relearn from scratch. So transfer learning and all these techniques, which are quite fancy, can speed up the process. However, basically, you need to understand that you still need a lot. And third thing, of course, that you need to learn about this is that whatever kicking you did on Earth, you'll never be able to kick on the moon. And one of the reasons is not related to AI. It's related to machine learning with the techniques that we're using. Why? Because to be able to kick on the moon, you need to discover gravity from the data. So we could discover gravity from the data, but we don't have today the mathematical tools. So this, of course, this is an appel to all the students to work on this. Why? Because gravity is what we call an invariant. Okay? So what it means, you need to do more tools which are the mathematical front related to topology, geometry, where you need to understand what does not change by translation, what does not change by rotation, what does not change by any kind of combination, so that you can look at where the invariant are. Clear for everybody? So of course, it's not because basically machine learning today is at this level, but it's because basically we're using a technique which is mostly based on regression and classification to do that. So there's still work to be done to be able to kick on the moon, but we're not there over there. Of course, by the way, the big success of AI is related to the guys doing speech recognition. So I'm sure there's a lot here of I wouldn't say senior people, but at least former professors, in which in the 80s, the big thing was about doing speech recognition. And the guys who did speech recognition spent time trying to model what we call the larynx here. You model it, and with the filter, high, low pass, whatever, it never worked. The day we understood that speech recognition was a classification problem, there was a big leap. We stopped modeling and said, okay, what are we going to do? Register. A lot of people talking. Next time somebody talks, we're just going to correlate or classify to which is the nearest. It made a big boom. The last thing also I think you need to be aware, either you work in telecom or not, is this problem of data. So data was mentioned many times. It's the oil of whatever you can think of. But there's one thing you need to understand is that the biggest success today in research in AI is done by industry and not by academia. There are some things, but if you look at all the papers which are published at ICLR, NIPS, things like that, they come from companies because they own the data. So of course you tell me, well, why don't they share the data? The majority of reasons they give you is reasons of privacy, meaning, oh, you cannot get the data because you'll discover some new things about our customers, things like that. I've been in companies. I spent 7 years at Huawei. I spent also working for Nokia and Alcatel-Lucent. That's only one part of the story. The main reason basically is the example I'm going to give you right now. So this is a plane. Okay, and I think you're seeing red dots. So this is known in statistics, by the way. So this kind of plane was the kind of plane which was stationed in England and going to Europe to bombard basically the Germans and coming back. And so the red dots that you see there are basically the bullets and the shots that the plane had when they came back. And of course, the commander of the base in England told to, at that time, they were not called data scientists, they were called statisticians. They told them, tell us where we should put more metal to reinforce the plane. So we're sure that the plane will not go down when they go. So of course, the guys smart, they look at the plane, they say, oh, well, we're going to put more here, metal here, a lot here, a lot here, and a lot here. Clear for everybody? But then, of course, the pilots came in and said, no, don't do that. Put metal exactly when there's no red dot. So of course, what are they talking about? How can you put more metal when there's no red dot? It's evident that every time the planes go, we count and we see always the planes. This is where they're getting shots. So of course, that was a big shock. But then the pilot said, there's something we didn't tell you. These planes are the planes which are coming back. There are many planes which are not coming back. Why are they coming back? Because they were shot in the cockpit. Clear for everybody? So they were missing data. So you had data, but you don't know the process of how that data was generated. Clear for everybody? So basically, when you give us data, I need to give you also the process of how it was generated. Okay? But now giving you the process is problematic. In the case that I'm giving you here, it would mean that I give you more information on where the planes were, how many planes I lost, things like that. In a company, is revealing the know-how, how we build that system. And the asset of a company is the know-how. So if I start giving you data, I can give you data, but basically if I start telling you how I build that data, I give you the experience of my engineers and I give you nearly everything I know. So this is very problematic. It has not been solved, but this is the main issue. And I had many requests when I was in industry asking me data, and I could not, because basically I need to reveal to you everything how we build the system. And that's a lot of know-how that I cannot give away. So this is quite important to understand that there is still this problem whenever you face, especially in academia, in getting the data on how basically you play with these two systems. Okay, I will not go on all these things, but these are more examples because I know that I was short in time in giving you a lot of applications that we did, and I'll just jump on that because it's not the most interesting for me. But just to tell you that in industry today, we're using a lot of these AI approaches to build networks better, to making them better. We're doing it at different stages at the network OEM, performance, businesses. We have also a lot of cases which showcase that you can work out. And I think today, whatever use case you have in mind, you can relook at it from a data-driven approach rather than model-driven approach. And I think many of the examples of my colleagues show that. Another thing I want to talk to you about, and there's going to be two messages, is basically the fact that the network that we're building can today enhance AI. We're building a supercomputer to connect the AI. Why? Because today, the majority that you saw today of people speaking around AI is a cloud perspective. What I mean the cloud perspective, meaning that you have all the computing and the data which is stored on one place. We are getting a lot of requests of people saying, I don't want my data to get out of my phone because of privacy issues, but you have also other reasons why data should not go back to the cloud. You have latency issues, if you look at the car business, for example. You have also basically problem of coverage, and for which today, the whole industry is pushing more and more to have things which are running directly on the device, doing learning on the device. But then doing learning and inference on the device is a problem because you don't have big data. You have small data on the device. And the question that you need to understand is how I can still basically do a system that does a big data learning out of small, massive number of data, which are small. So today, there's a lot of research which has been done there. There's a lot of frameworks which have been built with algorithms related to federated learning and others, which do what we call distributed AI. And today, how you build a massive distributed AI system is a big thing, because you need to connect all these intelligence where it's not anymore the data that you transfer, but what you have learned, the models. Clear for everybody? So how you connect the models that you have learned around that. And of course, this goes even more because the classical manufacturers, call them Intel, Huawei, and others, are building also the chipsets today to do it, meaning doing the learning directly. And here you have basically the capability of various kind of chipsets to do directly the learning or the inference, taking into account the complexity that you want to do that. Okay, since I don't have much time, I want to talk about a thing which happened to me, which was basically this quick win, long win, mid win that I was talking about. Is the story finished? Well, what I showed you until now is using AI for solving specific tasks. Okay? Meaning, yeah, you want to solve something and you apply it. By the way, the example I gave of shooting, I didn't give it randomly because in my domain, telecom, it's called beamforming, how you beam towards a user, and you need to find the right beam. And today we use techniques based on that called AI-based massive MIMO beamforming. So that's the kind of things that you use. So that was just a small comment I want to do. But of course, we're here on doing some kind of single task intelligence. One of the big aims that I had these last 2 years was, the industry is also moving around that, is to build something where you want an intelligence that does not do a single task, but do multiple tasks at the same time. Because we humans are trained not to just do additions perfectly, but we can do multiplications, additions, subtractions, and other things. So you could train a machine to be extremely good in one thing, but it's even better to train a machine to be good in many things, because this is the way we do. We could be you could ask anybody to do 1,565 multiplied by 1 million, that guy will be trained only to do that. But in general, we humans are trained extremely good to do many things, but not exactly this 1 million. So at the end, what you want to do is build up a brain. And by building a brain, depending on the disciplines, in mine, it's called telecom, I want to build a brain which manages the network completely based on all the data that you gather over there. Okay? And so this is a question I've been asking myself a couple of years. And in fact, to do that, this is where the quick win happened. I started looking at how I could build this brain, and of course, it's quite problematic. And these last years, I think people have not mentioned here during the conference this thing. There's a big tendency around the topic called large language models. I'll talk about it quite rapidly. It's quite magic. It's the ability to train models, not anymore for a single task, but models with billions of parameters, which can cope with multiple tasks at the same time. Okay? So when I arrived in Abu Dhabi, I wanted to do that. And I said to myself, how can I get deep into large language models and have that quick win so my bosses could let me do the long win? Because if I tell them I want to do telecom brain, the guy is going to say, this guy is totally crazy. What is the credibility he has to do telecom brain? And he never did it before. He wants to go on that. And it's going to take many years to do it because there's a lot of basically digital twin to build up on that, things like that. So what I said to my guys is, and I built a team. This is my team there, by the way. It's much bigger now. I'm there. I told them we're going to do something specific to the UAE where we're going to do some credibility around those topics. And one of the things that we found quite rapidly is that there was not a big, what we call large language model, which was existing in Arabic. The capability of building a super large language model in Arabic. You had one of the biggest 1 year ago was basically the one of the American University of Beirut, which had a high number, but there was nothing around that. And so I built up the team, and of course we did it. I called it also by the name of my daughter. It's called Noor. There you see it. And then what we did also, because you need when you do a research center to build a bit of visibility, we contacted Etihad News and told them, we're going to every week generate for you an article generated by this AI. And this is basically the article, which is now being published by Noor. So it's an article totally generated by AI. You give them the theme of this week, and then it generates based on what you learned. So just to give you things, but I don't think I have time on it. But I don't have time on it, but basically you have to know that these foundational models, nobody talk too much, but it's related to the big hype you're reading every time on the news related to OpenAI. Maybe you heard about ChatGPT, GPT-3, and OpenAI. If you have heard about it, this is the big trend at the moment. It's not anymore about doing single tasks, but doing these things which are large. It requires a lot of GPUs. And basically the things that you want to do are very task applications. You have to know that to train these models, today you have a bunch up there. Jurassic, GPT-3, Lambda, which are done mostly by companies around those things. And one of the three factors that you have to do is basically play with the number of parameters, the data size, what we call the tokens, and compute. Okay? Of course, how you do it has changed over time. In general, people tell you the bigger, it's the better. In fact, the bigger is not the better. What you need to have basically is also what we call the compute time. For example, today, one of the models which are making a big hype is called Chinchilla, that you can check, which has less billions of parameters than what you're using today related to Grapher, GPT-3, Jurassic, or Megatron Turing, for example. Okay? Now, I don't have time to do, but you train your guys. It's what we call a NLP, okay? For people who are not familiar with NLP, well, basically, it's natural language processing. It's at the heart of what people are using today. The idea of these systems is the following. You have a lot of texts that you generate. Of course, for my case, of course, what I want to do is a lot of data from the network that I'm putting there, and then basically learns how to manage the network. But here, basically, what you do is that it's optimization. So what are these language processing, not natural language processing, is that they give you basically the answer to a request. So you ask, the capital of the United Arab Emirates is Abu X. You don't know what is X. So you're going to learn what is the property of X knowing this context. This is what you're going to learn. You're going to learn that function P. Clear? That's what your system is going to do. You want to learn this probability function, or what we call this conditional distribution. And it's a neural network which is going to learn that for you based on all the data that you're doing. Okay? So don't have time also to insist on that. Today, the classical approach is based on transformers. That's what we built with the team. You also can't do what we call supervised learning because you cannot have somebody who labels. Maybe nobody insisted on that, but you have to know that the big hype about machine learning is based on supervised learning, meaning that you need, so just to give you an example, before in computer science, if you wanted to describe a dog, you told, a dog is an animal with 4 legs, with a queue, whatever, things like that. You take a kid, you put him outside, you tell him this is a dog. What if this is a dog? He'll never know what is a dog. Clear? However, if you take a kid and you tell him this is a dog, 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 and then you put him outside, he'll tell you what is a dog. This is called supervised learning. You need to label the data. You need to have a supervisor, me, that tells that this is a dog, and then he will learn what is a dog. And this has been a big parameter shift on how to learn. So it's not if, then else, is this, next time. Of course, the difference we know with the machine and a human is that a human, maybe you show him 20 pictures of a dog, he knows what is a dog. A machine, it's 1 billion pictures of a dog like this, a dog like this, a dog like this, a dog on the floor, on the couch, things like that, before the machine starts knowing what is a dog. Clear? So of course, these approaches, you cannot do it here because there's so much data. Who's going to be supervising things? By the way, just a little comment is that in Finland, a couple of years ago, you have companies who build data sets which are clean and labeled. It's a job, by the way. Okay, so you have people behind a computer who do, and in Finland they were using prisoners to do that, by the way, because in prison the guys have nothing to do, and so they put them pictures and they just label the whole day. So that was a big business for prisons to get money. And this is, by the way, now we have companies who clean for you, do this work that you're not able to do that. But I'm not saying that you should do this with prisoners, by the way. I'm just giving you this example. But in any case, I won't have time to go because I don't have much time. You have to know that we build a structure. It's based on these what we call kind of GPT systems. You need to fine-tune where basically you need to do some tokenizers. You need to do some embedding. This becomes more technical in terms of how you build it. Then you need to parallelize your things. Then you need basically to do some kind of multitask modeling of the whole system around that. And basically, you start building with training. Training in general takes time. It takes money also. You need to have a lot of GPUs to run these systems when you start from scratch. And this is what we did today. We trained basically a model with 13 billion parameters. What we have released today, because it cost us to do that, and we want to sell that kind of big model, we released an open version, or you could call it open source version, but all reduced. So you can play with that, by the way, on going to this website, I'll give it to you, and you start playing with that, but you will not have the great performance of what you could do. Well, what is a large language model for your information? It's this kind of things. So by the way, you can go on this website here of my daughter and start playing with that. But basically, this is what you do. So first of all, what you could do is do summarization. Okay, these are what we could do with large language model. It's finished right now, by the way. Large language model, you do summarization. So here you have an example. I'll put a text, and there you'll have in Arabic the summarization of that text. So you take any big text, you put it, and you have a summary of it. So you don't need to ask anybody to do that. You have a summary, you say the number of lines you want, and it does a good summary. So you can read it, and that's exactly the kind of summary that you have. So that's extremely fancy as a system that you want to do. Okay, you have many books that you need to summarize. You don't want to read them. You say the number of lines, and it summarizes the text. Second thing, you want to create a story. So you ask the machine, you can read there, to basically provide you a cat. This is a cat. You do a text. You write basically what you want, and then it generates you a story. This is what we did, for example, for the articles. We tell them talk about COP27, blah blah blah, and then it writes you text. You'll see right now. We'll wait. Up, and then it writes you a whole text generated from basically a statement that you want to do. And you can play a lot of things like that. For example, you want to write a public press release. It's hard to write a public press release. You know, in general, it's quite structured. You just tell, this is what I want to announce, blah, blah, blah. You put it, and then it creates you the public press release that you want. I give you this example because this is what we call a quick win, meaning that you want to build something called the telecom brain, where you want to build this whole system where you're going to do it on another topic, but then you want to get some credibility to showcase to the people that, okay, this is something you can build and work out and make basically a bit of visibility in order not to have too much pressure from your bosses. And so they give you time, basically, so you can build your whole system. I'll stop here. I'm really sorry for the time, but I think I took 1 hour. Okay? I took more than 1 hour? Okay.